questions today. We'll start off. Anybody have any questions about first sets, follow sets, anything we've covered so far? Questions on project 3, homework 2? Anything? Yeah.
Yeah. So you did last class. You did the follow set example with emails.
Yes.
You started talking about parsing. Predictive,
Yes.
And you were talking. So does each token have its own parse function? What has its own parse function?
So what we're writing here, and that's what I'll put this up here since this is where we left off last week or on Monday. So what we're writing here is parse functions for every non-terminal on the grammar. Exactly. So we want to know how we're going to parse an input string based on our lexer by getting tokens from our lexer. We're going to say, okay, well we know we're going to start at the starting non-terminal. That's why we started with parse s, the starting one. And then by looking at the first terminal, right, we should be able to determine, well, which of the rules that s produces does this string correspond to? Or does it, this string or token, does it correspond to syntax error? So it's not a string in our language. So that's what I think, I want to say in the next one of these parse functions, we'll look at what happens when we get to a terminal. Because right now we've only been parsing non-terminals. Any other questions about where we are right now before we continue? Yeah.
For the homework, do you want us to just model it after this, or do we need to have like actual return values or anything like that?
So for the homework, you can model it after this. This is really what we're looking for here. And it should be valid-ish pseudocode. It doesn't necessarily need to compile. If you forget like a semicolon, we're not going to gain you points. But if it's completely wrong, if, I don't know, no braces, or if it doesn't make sense, or we can't read it, then it's going to be wrong. So yeah.
For the project, I was looking at the first sense of just like getting the input grammar and trying to define it.
Yep.
And it looked like you couldn't make a recursive set parser with it.
I'd have to look at it directly.
Because there's some ambiguity in it. So I was wondering if that's intentional.
So yes, it's intentional in the sense that it's not going to change. You can write essentially a custom parser for that. So you don't need to do any, it doesn't need to be in this format like we're doing right here. Any other questions? All right. So as we can see on the board, where we left off was we were looking at the function parse display name list. And remember here, at the very top, in the top left here, we have the rule. We have display name list goes to a word followed by a display name list, or display name list goes to epsilon. And so we already went through, we've calculated first and follow sets for everything in the grammar. So by checking the next token, by calling get token, we can check and say, well, is the type, if it's in the first set of word display name list, well then we know that that must be the rule that we've chosen. Or that's the parsing rule that generated this string. So that's why here we check if t-type is atom or quoted string, then we're going to put that token back, unget it, and then call parse word, parse display name list again, and then print out to say, hey, this is the rule that we chose. Otherwise, so the other rule, right, there's two rules here. The other rule is display name list goes to epsilon. Now, if that production rule or when that production rule is chosen, right, there's going to be nothing in the resulting string, the resulting tokens. Right? There's no token that corresponds to epsilon. And so how do we know if that production rule was taken? And the way we do this is we check the follow set of display name list. So what is the token that follows display name list? And that's what we calculated with follow sets. So that's what here we're checking if the t-type is equal to a left angle bracket, then that means that this is the epsilon production. And so what we do is we unget the token, right? So we put that token back because we're not parsing that token. And then we don't do anything else because there's nothing else to parse because our production rule is display name list goes to epsilon. So there's nothing for us to parse or to consume from the input. So then we just return. Otherwise, we're going to have a syntax error. So questions on this one? Before we continue? Yeah.
So if the first word contains epsilon, once that contains epsilon, does that mean you also have to everything in display list is an t-type?
So So if the first is in this, if the epsilon is in the first set here of word display name list.
Yeah.
So if that was the case, then, so for one of the rules, there's two rules for deciding if the grammar has a predictive parser, right? And so the first rule says if you have a rule that A goes to alpha and A goes to beta, then the intersection of the first sets of alpha and beta better be empty. So in this case, right, so here we have A as display name list, we have alpha as word display name list, and we also have a rule where A is display name list and beta is epsilon. So we actually, when we started this, it was obviously Monday, so it was a long time ago, but we looked at this and we took the first sets of each of those. We said, what's the first set of word display name list? And what's the first set of epsilon? And is there an intersection between the two? And we showed that there wasn't, so we're not going to worry about that. But if there was, then we'd stop and we wouldn't generate this predictive parser. We wouldn't be able to say that, hey, this grammar has a predictive parser. Yeah?
Show the predictive before just after get the predictive.
In this else if clause? In this case?
Yeah. Because it's a recursion.
So, yeah, so this is, we actually don't know until we've parsed a word and parsed a display name list, we don't know if this production rule is correct. Because it could not be a word, or there could not be, this display name list could be wrong. Because we've only checked one token ahead to make sure that the next token is valid, but there could be multiple tokens there. So that's why we wait until both those functions return to say, hey, we know this rule was chosen here, and it successfully completed because control flow came back to this point. Great. Other questions? Okay. Great. Okay, so now we're going to move on to the next function. So this is the first one we'll see that has terminals in the production rule. So here we're going to talk about parse angle address. And so the rule here is angle address goes to left angle bracket, address specification, right angle bracket. And so we've calculated first and follow sets for all these things here. And so our function, we're going to do very similar things, right? The first thing we're going to do is we call getToken, because we want to make sure that this is a valid string that was generated by this rule. So what are we going to check the first set of? Are we going to check anything? What are we going to check? So we want to raise a hand? Instead of all shouting at once. Yeah.
The first set of brackets, address specification bracket.
Right. So yeah, it's very mechanical. So we check the first set of the entire thing on the right-hand side, which in this case is left angle bracket, address specification, right angle bracket. And we know that the first set of that is the left angle bracket. Right. It's a terminal. It's all, whatever that string generates, that first token is always going to be a left angle bracket. So we check, is the type of token that we just saw equal to the left angle bracket? And then what do we do next? So I guess the question is, what do we traditionally do? Yeah. Yeah. Do we do ungetToken here? You want to say that louder?
It's going to consume the less than sign and go to address specification.
Yeah. So specifically here, we don't call ungetToken because here this is a terminal in our string. So this left angle bracket is going to be in that resulting string, right? It's a token that we care about. So we actually want to consume that token and start parsing right after that left angle bracket. So we're not going to push it back and call ungetToken. Awesome. Okay. So then we're going to call parse address specification, right? So we're going to recurse into and call that function. It's going to do something. And then what do we do after that returns?
GetToken again.
GetToken again. And what are we going to check?
We need to check if it's the other side of the angle bracket.
Right, so the right angle bracket or the greater than symbol. So yeah, so I kind of did this kind of the opposite way. Here we're checking for a syntax error, right? So we know if we saw a left angle bracket and then an address specification, if the next thing is not a right angle bracket, then we have a syntax error. So that's what I'm checking for here is, hey, if the t-type is not a greater than symbol, then there's got to be a syntax error. Then once all of those checks pass, right, now we know, okay, this is the production rule that we correctly parsed. That means this is where we're going to print out that this is the production rule that we just parsed. So does everybody see why, once again, we don't call unGetToken after we check the greater than symbol? Right, because that is a token that we want to consume. Questions? With this? Alright, so what do we check if, what do we say if it's not a left angle bracket when we first got that first token? Error, right? Yeah. There's no other rules. There can be no possible thing. It's going to be a syntax error. It's an error if there's not if we're trying to parse an angle address and there's not a left angle bracket. So that'll be a syntax error. Questions here? Yeah.
When you call GetToken for address spec, do you also consume the right angle bracket?
So when parse address specification calls GetToken, or where?
Yeah, when you do parse angle address, you enter the first if statement and you call. Oh, never mind. Got it. Never mind.
Okay, good. Yeah, so you can kind of think about it, this is why, so each function in isolation is going to consume only those terminals that are contained within its right-hand sides, right? So this is why the only tokens we consume are left angle bracket, and then we're going to let parse address specification do and consume whatever tokens it needs to consume, so it will move the lexer through the sequence of tokens until it comes back, and then we say that next token right here better be a right angle bracket, otherwise there's a syntax error. So then we consume that, and then we return, and we say, okay, we've properly moved through the input, the sequence of tokens to capture this parse angle address. Yeah?
What is parse address specification returning though? Because you're just running it as a function. 'Cause what if it runs into an error and it prints out like an error statement or something?
So
Is
part
that
of, yeah, so it's
that's
part of the
program or does it what?
So it's part of the semantics we define here that syntax error is going to halt execution and just output an error. So we know it's not going to return unless it was successful by parsing. Actually how you implement this can vary, right? You can have this parse address specification return something if you care about what it returns. You can have it manipulate data, some global data. You can have it build a tree. Actually, each of these steps could build a tree, and so you can actually build the parse tree directly from here. So yeah, really, however, it's really up to you. Is there another hand in this direction? All right, cool. Okay, and now we keep going. So now we go on and we see how address specification works. So we know that address specification produces a domain, I forgot what the first A is. Atom at, yes, okay, it's my own name, that's different. Okay, a domain atom at followed by domain, or a quoted string at followed by a domain. So we calculated first and follow sets here. So what's the first thing we're going to do in this function? Somebody? Yeah. Yeah, get token. We want to get the token. We want to see what the next token is, right? It's the same thing. Because we need to know which one of these rules to take. So we call get token, and what's the first set that we're going to check? What are we going to check? Somebody, I heard it. Yeah.
Domain atom at.
Yeah, domain atom at. So we're going to check the first set of, remember, domain atom at followed by domain, because that's the entire right-hand side of that production rule. And we know that that is domain atom at. So we're going to check if the type is domain atom at, what's the next thing we're going to do? Someone raise their hand? Go. It's okay to be wrong. Yeah.
Get token.
We're going to call what?
Next token. Get token.
Get token? Why? What are we going to check with that token?
You see, basically we are consuming this token, and
Mhm.
we are trying to see if it matches with the second part of the rule.
Right, so what's the second part of the rule here?
Domain.
Is domain a terminal?
No.
No. So right, so we're gonna, so
So we're passing this token.
yeah, so you're right in that we're not gonna call unget token, right? Because we've consumed that token. We want to consume the domain atom at token. But what we're gonna do next, right? We're gonna let, because we know we've chosen this rule, because there is a domain atom at, we don't need to check any of the first token in domain. We just call parse domain directly, so it can parse however it needs to parse. And then when that returns, now we know this is a proper domain that was just parsed. So now we're going to print out that, hey, this is the production rule that we chose here. Any questions on that branch? Okay, what are we checking on the next branch? Somebody over here? Yeah. QSA, yeah, so quoted string at. So remember, once again, we're checking the whole thing, the first set of quoted string at and domain. And we're going to check, hey, if the T type is a quoted string at, then what are we going to do? Say it louder. Parse domain. Yeah, parse domain. Okay, so yeah, so we've consumed the quoted string at of this production rule. And we don't want to put it back because we want to actually consume that token. And then we're going to call parse domain, which will then recursively go and parse whatever it needs to parse. And then we're going to print out that, hey, this is the production rule that we took. Address specification goes to quoted string at followed by domain. What do we do if it's not one of these two strings? Syntax error, right? It's got to be an error if it's not one of these two strings. Questions on this? Kind of feel like you're getting the hang of it, the intuition here? Yeah, awesome. Cool. Okay, we'll have a few more, so that should be good then. Okay, so we have the very simple rule, domain goes to domain at? I think it's domain at, right? Dotted at, okay. Dotted atom. Dotted atom, okay. So what happens when you use these shorteners? Okay, so we're going to write the function parse domain. What's the first thing we're going to do? Get token. Yeah, we want to get the token, right? And then what are we going to check?
First set of DA.
Yeah, the first set of DA, so the first set of the entire right-hand side. And we know here that it's just dotted atom. So we're going to check, hey, if the T type is equal to dotted atom, then what do we do? Yeah. We print the rule. Why?
Because there is nothing after.
Why don't we call unget token?
Because
Or do we call unget token? Great question.
because we have to create
Right. So yeah, so we've called get token, we've consumed a token. We know that this type is the type of this one rule that we have. The rule is domain goes to dotted atom. And so we're done, right? We don't need to put anything back. We don't need to recursively call any functions. There's no non-terminals here. So all we do is print out, hey, we match this rule. Yeah.
Just to avoid confusion,
Yeah.
the comment after T-type get token should say check first of domain, right?
No, it's always the right-hand side of the rule. Because there could be, if there's multiple options, you want to check the first set of the entire thing. Remember, in this case, it's only one rule, right? So it's the same. But if domain had two production rules, the first set of domain includes the first set of both rules, right? So we want to disambiguate between the two rules. And so the other, yeah.
I want to ask that should we check for end of file after checking whether T type is PA or not?
So the question is, should we check for end of file? So why would we check for end of file?
Like after like domain there is a terminal, and after that,
You mean because it's in the file set here, maybe?
yeah.
So it's actually one of the things we could check for, but we're gonna let something else check for us, basically, because we know that we're not actually the end of string, right? It could be an end of string after us, there could be something else, but we were called somewhere, so we know, hey, we consumed our domain by consuming that domain atom, so we'll let whoever else deal with that. Okay, so what do we do if it doesn't match, if it's not a dotted atom? Syntax error, right? It's an error. It's got to be, if we're trying to parse a domain, it's got to be a dotted atom. Yeah.
So what is unget token called again?
So
Under what circumstance?
you want to call unget token. You want to put the token back when you're not actually going to consume it. So, and when you want to consume it is when there's a terminal in your production rule. So a terminal means, hey, that token's going to appear in the sequence of tokens, right? So we want to consume it to move our lexer to the next possible token. So basically, the kind of idea is, hey, if the next thing is a non-terminal, then you want to put that token back to let that non-terminal parse it however it's supposed to parse it. You just use that token. You peek to that token to decide which of these two rules apply. Cool. All right, so we got one more, I think. Word goes to atom or quoted string here. We have first and follow sets. So when we parse word, what are we going to do right off the bat? Get token. Yeah, we need to get the token. We need to peek at the token to know what to do. So what do we check? What are we going to check first? T-type of what? Against what? Against atom, yeah. So we want to disambiguate between these two rules. So we're going to check the first set of atom, in which case it's obviously just atom. So we say, hey, if the T-type is atom, then what do? Do we unget token? Do we call some other parse function? Print. Yeah, we just print. Right? Maybe it's kind of easy to tell because of the space here, but you know. Yeah, if you think about it, right, we want to print because we're done. We've consumed that input token, we've moved the lexer forward, and we've parsed a word. We've done what our function wants to do. Now what do we check next? Do we just say else syntax error? T-type is what? You saying something? Somebody want to actually say it out loud? Yeah. Quoted string. So we're going to check first a quoted string, right? Because we want to disambiguate this rule. So we're going to check, hey, if the T-type is equal to a quoted string, then what do? Print. Yeah, we want to print. Say, hey, we got this rule. So this is the production rule. Word goes to quoted string. Okay, what do we do if it's not either of these two tokens? Syntax error, right? It's got to be an error because a word will only generate either an atom or a quoted string, nothing else. So if you try to parse a sequence of tokens and you're trying to parse a word and the next token is not an atom or a quoted string, that's a syntax error. Yeah, yeah.
When do you check for follow again?
So you check for follow if there's an epsilon in one of the first sets. So if there's an epsilon in one of the rules. So if it could produce nothing, the only way you have to tell of which rule to take is by looking at the next token and checking it with the follow sets. And so the checking and the disambiguation, it follows directly from the rules we have for deciding if you can have a predictive parser, right? You can have a predictive parser if there's a difference between the right-hand side's follow sets, right? That means you can choose which rule, so that's why we always check. And the second rule is if you have a rule where A goes to epsilon, then it better be the case that the first set of A does not intersect with the follow set of A. So this is a way you can tell, hey, is it one of the A rules or is it the next one? In which case it would be epsilon. So they're very linked here. Okay, and so, I didn't animate this slide. So this is my thought process of how, kind of like a very high level thinking of this is how you write a predictive recursive descent parser. You're first, for every non-terminal A in the grammar, you're going to write a function called parse A. And that's exactly what we've done here, right? Because we want to parse non-terminals. And then for each production rule, A goes to alpha, where alpha is some sequence of terminals and non-terminals. We check if get token is in the first set of that sequence of tokens, right? So that's what we're checking with every if statement there. Hey, if it's in this set of if the next token is in this set of the first set, well then we know we should choose this rule. If it's in the other one, then we know we can choose that rule. If it's in none of the first sets of any of the rules, then we know it's a syntax error. And then for every, here I have terminal and non-terminal A in alpha, so we go through, right? So we want to parse properly that right-hand side rule here. So if it's a terminal, we just check that, hey, this is the correct token that we expect. If it's a non-terminal, we want to put it back, and we want to call that parsing function. And the last rule, yeah, is just the syntax error. So if it's not in any of the if it's not in the first set of A, which means it's not in the first set of any of the right-hand side rules of A, then it's a syntax error. You just do this for each of them. Oh, and this checks, let's see, get token, right, is not in the follow of A. So yeah, this handles that alpha, the epsilon production rule. Where we have a rule that A goes to epsilon, we know we need to check the follow set of A to make sure that that's the rule that we choose. Otherwise, it's the syntax error. Questions on this? Yeah. If first of alpha contains epsilon for this right here, so that would be this rule right here. So I have a special case rule here for if alpha is equal to epsilon, then check that get token is in the follow set of alpha of A. So that's checking whether that rule is in there. I may have to revise this to see if this, huh? So if, yeah, I think I should probably change that to, yeah, if it's epsilon is in the first set of alpha, yeah, that's correct. You have to check the follow of A. So there'll only be, yeah, so there will only be, so by the two rules, right, there's only going to be one rule that has epsilon in its first set, right? Because the very first rule of the predictive parser says that the first sets of all the right-hand side rules must be disjoint. So only one rule is going to have epsilon in its first set. And then if that's the case, then you'll be able to tell if you take that rule whether it's in that first set or it's in the follow set. Yeah. Oh, you would print that rule, because that is a rule, right? It would be, if it's A goes to epsilon, then you would print that rule. If it's, you print whatever that production rule is. Exactly, yeah. So I'll make a note to update this slide before I post it. Any other questions here? Yeah.
So when you mean that they have to be disjoint, you just mean that there can't be two epsilons in the first set of any. Okay.
Exactly. Yeah, that's what that means, right? So you calculate first sets of one right-hand side rule, the first sets of the other right-hand side rule. If there's any element in common, like that would be disjoint, right? They have to be completely different sets.
Okay.
Yeah, nothing in common. Whatever way you want to think about that. Any questions? All right. Cool. I'm sure as we get closer to homework 2 turn in, there'll be more questions. Okay, a little bit. I know I literally just said it, but any other questions before we move on? Anything to do with parsing? Okay. Cool. So now we come to the question. Yeah. Dude, I just started. Just kidding. Go ahead.
Do all syntactical errors come from predictive recursive parsing?
No. Not. So syntax error just means that it doesn't conform to our grammar. So the predictive part there means that we can, that's why we always call get token, is because we're going to look at the next token that's there in our grammar, and we can decide which rule to choose. The other way to do it is actually what the Mailgun folks did when they did their parser. It's not predictive, it actually tries all possible parsing combinations. So it says, hey, first try to parse it with these rules. If that fails, then try to parse it with the other rules. And if we tried all the rules and all possible combinations, then fail. Then that's a syntax error.
So would you only do that when there isn't disjoint?
Yes. Yeah, so you would do that if there's not a disjoint, if there's common elements in the first set. So yeah. So actually if you take their grammar that they have for email addresses, you'll find out that it's not predictive because of that reason. So that's why I had to introduce those extra tokens so we could disambiguate.
Okay.
Yeah.
So would that be ambiguous for regular language?
So I don't think so. So it's definitely not, it's not a regular language because regular language is regular expressions, right? So I don't think that language can be described by regular expressions. So ambiguous is two different parse trees for the same string, which is different than predictive. Predictive means we can choose which one. I'm fairly certain you could have a predictive grammar that's not ambiguous. So always give you one tree, like one of the trees will be correct. It's just that you don't know just by looking at the next token. So yeah, that's what it is. So it could be that by looking 2 tokens or 3 tokens ahead you could tell, but for our purposes that gets very, very complicated. It's not as clean as this. So that's why just by looking at just the next token. probably have to, I think you'd have to introduce new tokens, because that's really the problem, is you can't tell just from the tokens that you get back which rule to choose. So you could either, maybe able to add more grammar rules, but I don't know if that would always be the case. I think it would depend on the specific grammar. Let's go back, yeah.
For first and follow sets of homework, we have to show every step for each one like you do in class, or if we know that it's not going to change in the next pass, we have to show that.
So I guess it would be about how clear you are, right? So for the homeworks and for exams, right, it's all about us being able to grade your work. So if you write, so let's say you have one step and then you say, this is never going to change because of X, Y, and Z, that's totally good because you're explaining your thinking there. So yeah, it makes sense not to write those extra ones. Otherwise, you still are calculating, you're applying all the rules there, it just doesn't change. So you can also just write them. Yeah.
So predictive grammar is basically for unambiguous grammar, right?
Yes, your grammar has to be unambiguous to be
Yeah,
predictive.
so are we using the leftmost derivation? We are, I think, using the leftmost derivation, right? In our this thing, predictive grammar. So can we use the rightmost derivation as well?
Possibly. That's a good question that I'd have to look at a lot more. I don't know the answer off the top of my head. So I think that we are doing the leftmost grammar because we always are recursing to the left.
And we are checking for the follow set, right? So probably from left to right we are checking.
Right, so we're consuming the inputs from left to right. So could you start from the other way? Probably. I don't think it would change things significantly, so I'm not going to say yes or no. Any other questions? Cool. All right, so now we get on to semantics. So now, up until now, we've seen that, so we looked kind of just to make sure we're all on the same page, right? We've looked at lexical analysis, right? So that's all about defining how to turn a sequence of bytes into a sequence of tokens, right? So we've seen how to define regular expressions, and we've seen how to apply those regular expressions, how to disambiguate when there are multiple regular expressions that match. So we know how to go from regular expressions that define tokens into a lexer that's able to pull those tokens out. So then after that, right, is syntax analysis, where we're concerned with specifying valid sequences of tokens and specifically turning these tokens into a parse tree. So with semantics here, it's very kind of logically related, even though it seems we're maybe shifting a little bit. With semantics, we're concerned about, well, what does that parse tree mean, right? So up until this point, we don't really care what we're parsing. When you're parsing an email address, right, you just have terminals and non-terminals, and you can write a parser for that, you can parse it, but it's parsing words and domains and domain atomats and quoted strings, right? You don't really care what it's parsing. You can write a parser for it and be able to parse it. So with semantics here, we're going to actually go ahead and talk about, well, how, for a programming language, can we define what the semantics are? What's the meaning behind the language constructs, or the meaning behind this specific operator? And what things are valid in our language and what things aren't valid in our language? And kind of, we're going to look at the interplay of, well, if you design it in this certain way, that means there's things you can do when you're compiling it that maybe you can't do in another way. Questions? Okay, so we want to define a programming language. So we've written all this parser stuff, we're able to get a tree from it, but what does that mean? So how have you seen language semantics defined? So like, how did you learn Java? Or, yeah, let's go with Java. Is that like the first language that you learned here, mostly? Yeah. So, anybody remember how they learned it? Banging your head against a wall or your computer until it, yeah.
Yeah, pretty much that. Just constantly I taught myself Java, so it was a case of check the wiki, try to code, check the wiki, try to code.
I've definitely done that as well.
Segfault.
What about in class? How do they teach you in class? Yeah.
Relating it to something that you already know with pseudocode.
With pseudocode? So, implement something you already know. Wait, say it again?
Explain it by relating it to something you already know using pseudocode.
Okay, is that how you learn Java?
Well, I mean, I started with Visual Basic.
Okay, awesome.
Yeah, I mean,
We won't judge you, don't worry.
I'm not proud of it.
Okay. So you relate it to kind of some pseudocode maybe that you know, or you kind of relate between like, okay, this is the Visual Basic implementation of this kind of pseudo algorithm, and so you kind of try to, I'd say maybe kind of like learning by example in that case, where you kind of are looking at examples. What else? Maybe like read a book. You just read the book.
They would give us like samples of code, like afterwards, which is memorize certain sections of it that you're not supposed to understand what they mean, focus on one small part, and like build it from there.
Okay, yeah, so kind of like just memorization. Like, here are the rules. They were given down to us from up on high from, I think, James Gosling in the case of Java, right? So, you just learn them and apply them. Anything else? Anybody read like the Java specification? Say it like it's a joke. It's a real thing. Yeah?
Learning about Java concepts like class and inheritance and then predicting the pseudocode.
Right, so they kind of teach you the various concepts in the language by examples, probably in class. So yeah, you could read there is a language specification for Java. We'll get into it. But what properties? So what properties do we want from language semantics definitions? Like what? So I tell you, I just invented this really awesome programming language. It's going to change your life, and you're going to go be able to write this awesome, create a startup around, use this language, and you're going to be 10 times faster than your competition and half the memory, 4 times the speed, whatever. So you say, that's awesome. I really want to learn that. How do I know what your language is and what it means? Right? So how would I tell you or give that to you? What would you want from that? Yeah.
Different variable types.
Different variable types. Something more high level, right? So like, I don't know, would you like one way it would be like, I just write it down, right? I give you and I say, hey, here's what everything in my language means in English. Is that good? Would you like that? There's not a wrong answer. You have your hand like kind of 3/4.
Like an API. APIs are nice.
Yeah, like an API, maybe like documentation. So I give you documentation on the API. What about the language itself, right? Like how do you know how to write a program in that language?
Because you want words to be descriptive.
You want the words to be descriptive. Yeah, so and sometimes we want it to be precise, right? We want to know. So descriptive, I'd say, is kind of another word for precise, right? We want to know, when I write this code, what is it going to do after my program, it gets compiled and executed, right? So what does this code mean? So I'd say preciseness. What other types of things do you like? Yeah. Consistency. Yeah, so that's kind of I'd say that's a language design goal. Is you want, I think they call it the principle of least surprise, right? You don't want to use the ++ operator and have it do something completely different in your language. I would say for terms of documenting the language semantics, I'd say you want some type of predictability, right? So that you can read the specification or understand the semantics and then look at some code and say, aha, I know exactly what that code's going to do based on what this document that the professor's given me says, right? So you want some form of predictability. What if I just gave you a 1-page document? Would you be suspicious of that?
Yes.
Why?
Because I feel like it wouldn't contain. I feel like there'd be points where I'd be like, well, I'd have to guess what you're trying to think.
Right. So yeah. So you want, as much as we probably dislike going through 100-page documentations of programming language specifications, the flip side of that, if your specification isn't complete, then you know, you may be able to write it. You say, hey, this program that I can write is syntactically valid, but your specification doesn't say what it should do or how it should operate. So what's going to happen when I run this? What's it going to do? Is it going to do anything? Is it going to explode? Is it going to do the right thing half the time and the wrong thing half the time? Is it going to depend on what compiler I use? So that's another thing, right? So if you have other people who take your specification and try to implement a compiler for it, is it going to be the same? Are you going to be able to write the same program and have it run the same twice? So we've kind of been hinting at it. So what are some ways that you could specify these semantics that hopefully have some trade-offs between these kind of three properties? First person can use maybe the example I've already given. Yeah.
Complete documentation.
Yeah. English. Use English, or I guess, you know, whatever language you're most comfortable in, but kind of the standard technical language is English. So write it in a human language, specifying exactly what the semantics of your program are. Any other ways? Is this the only way? Yeah.
Pseudocode.
Pseudocode. You want to explain that?
Just eliminating the depth of it and like showing the basic layout of how a program should look using the language.
Maybe. It may be related to the, well, to one of the examples. We'll see. What about, do we know how like Python started? So, God, I can't, oh, yeah.
Was it readability? They wanted.
Almost. So it's definitely, so it's not an English specification, right? So can I don't know, can I define a new language if I don't have a specification or documentation for it?
Encapsulation.
Encapsulation and what?
Like you encapsulate different things the same way, consistently.
Okay, well, I'm thinking more in terms of deliverability, right? Or how would I communicate my specification to you? Like I want encapsulation, those kinds of things. But one way I could do that is write a big documentation. What would be the other way? Yeah.
Compare it to like you're using another language to build it, you can compare it to that language.
That's a good one. I haven't thought of that. Yeah, it's actually, I also think, related to the third one. So yeah, you could relate it to something that people already know. Yeah.
Maybe do it through implementation.
Yeah, so implementation, right? I just give you the compiler and say, bam, here's how this language works. If this program compiles it, it's a valid program in that language, and whatever this compiler does with your program, that's how it should do. That's my language. So yeah, they call it, that's called a reference implementation, right? So that's, honestly, that's how a lot of programming languages start. So, you know, you're kind of developing this toy programming language for yourself, and you think, maybe people like this. Well, here, hey, this is some compiler for this language I wrote. Here it is. There's not a lot of documentation, but what the implementation, what the compiler does, or what the interpreter does, that's what the programming language should do. Okay, so the third language is related to some of these other concepts. Yeah?
So what you're saying for that reference implementation is you give someone like a block of code that shows how to use the if statements, all that kind of stuff, and they branch off of that? Is that what you mean?
No, I mean, you give them, so if you think about it at the basic level, you give them no documentation, you give them a program. You say, here's my compiler. Whatever this, so you can also easily specify the syntax, right? So you can say the tokens, you can give them the grammar in exactly the format we've been looking at. That's how people define grammars. So those are very easy to precisely specify. But the fact of what it does, so what some people do is say, hey, here's my language, here's the compiler form. Now obviously you'd probably also give some examples or something to get people started. But the fact is that like it's not a Python program unless it runs on the Python, the standard Python interpreter. Or at least it used to be. It may have a specification now. So what would be maybe the third way? So it's kind of been related to it. It's kind of related. Anybody here like a math major? No? Yeah? So yeah, we could actually formally define our language using math. We can specify the exact semantics of what every single operator and construction in our language is using formal language. And so we'll look at some examples. So I pulled up anybody want to take a guess at how long the latest C documentation, I don't know, no, it's not the latest, this is C99 that I found. Anybody want to guess how long it is? Is there like a higher or lower gain? Yeah,
500.
higher. 1,000 lower. All right, now we're just doing binary search. So 538 pages long is the specification. And it contains language like this. An identifier can denote an object, a function, a tag, or a member of a structure, union, or enumeration. A typedef name, a label name, a macro name, or a macro parameter. The same identifier can denote different entities at different points in the program. A member of an enumeration is called an enumeration constant. Macro names and macro parameters are not considered further here because prior to the semantic phase of program translation, any occurrences of macro names in the source file are replaced by the pre-processing token sequences that constitute their macro definitions. So if you really study this, it definitely makes sense with what you know about C. This is one paragraph that defines what an identifier is. This is what an identifier means in C, the standard. So what would be some problems with using English? Or some benefits? So yeah. Yeah, you don't know how to actually use it. Yeah, maybe if there's, I'd say maybe if there's not any examples, it would just be a lot of language like this, and you'd read the whole thing and be like, okay, I don't really know, what am I supposed to do here? Yeah.
It sounds like it's describing one of the compiler is, but not giving a definition.
So, and it may be, so remember this is just one paragraph that I took. There's like 4 after this, just in that one section that probably clarify exactly what an identifier can be used for and what it means. And I guess this is specifying what things an identifier can denote. Hopefully at some point, right, there will be equally long definitions for an object, a function, a tag, and a member of a structure, union, or enumeration, right? All of these things have to be precisely defined. You can think about it like this is kind of legalese for programmers, right? Because if there's any ambiguity, right? So what happens if there's ambiguity? What if just an ID is a thing? It's like a name.
You don't know what the compiler is going to do when you feed it that.
Yeah, so we don't know as a programmer what the compiler is going to do when we feed it a program. And if somebody else, if I have Microsoft writing a C compiler and I have, who else writes a C compiler now? It's Apple kind of the open source community, I guess. I don't know, is it GNU maybe you'd say? Like GCC, right? So if they both say, well, no, I think a thing is this, and they say, no, I think a thing are these things, then now you have two different compilers that compile programs differently, and in effect you maybe have 2 different languages. So you have a huge headache and problem there. So yeah, it could be ambiguous, it could be ignored. So like, you know, this is just a piece of paper, or not even that anymore, right? It's just a document, a PDF somewhere that some committee agreed is like, hey, this is the latest C standard. But if any compilers implement it, does it matter? No, yeah, right? So you know, you can specify that if it's a C program, it's got to do X, Y, and Z. Well, the compiler writers are lazy, and nobody writes a compiler that does that. So you know, language feature is gone, even though it's in the specification. What about not correct? So does that ever happen to anyone? I hope not, but yeah, what if the compilers themselves could have bugs, right? So if the compiler has a bug that doesn't conform to the specification, and you're trying to use that compiler, well, you know, you're kind of out of luck, because they, you know, maybe you file a bug with them, but yeah, it could be, you could read the specification, know precisely what it should do, and have that not be the case. And so we kind of talked about this is kind of about completeness, but what about something that the specification doesn't mention? Is that a good thing? Is it a bad thing? Have you ever encountered that in your programming careers? Anybody? Yeah? Oh, yawning? Good sign. So we're actually going to see an example of this later, right? But there's certain cases where you can write a program that's syntactically valid, but passes type checking and everything, but still contains undefined behavior. And so maybe on some compilers it does one thing, in some operating systems it does one thing, but in other languages it does another thing. So this is like the trade-off between, well, if you made the specification 1,000 pages long, could you identify all those cases and what exactly they could be? But is anybody going to read that 1,000-page document? But yeah, I'd say specifications in general, English specifications are good for having multiple implementations of the same language. Because you can say, well, everybody should code it to this spec, and then you kind of fight about what the spec means and hopefully clarify things and come to a consensus. But it's a long, difficult process. Okay, any program Ruby? Touched any Ruby, some people? Okay, so up until 2011, Ruby was specified by a reference implementation. So Mats is the name of the guy Japanese guy who created Ruby, and they had documentation, but the specification was, hey, the semantics of the Ruby language are defined here by this Ruby interpreter, Mats's Ruby interpreter. And so that, any program that the reference implementation runs is a Ruby program by definition, and it should do whatever the reference implementation does when it executes this program. So what are some of the pros and cons here? If I give you a program, let's say you have some minimal documentation, but if I give you a compiler or an interpreter, what are you going to do with that? Is it good? Is it bad? What do you think? Yeah?
Well, it stops the problem where what we had in the past with just English documentation where there could be multiple interpreters, and now there's only one to deal with.
Yeah, so it's very, I'd say, it's precisely defined, but the caveat is if on a given input, right? So the trick here is you actually have to, so if you have any question like, what does this language feature do in this really weird circumstance where I don't know, take an address and then add a class to it and then execute the class and then call some eval, whatever. If you have any question, you can actually write a program that does that, run it on the reference implementation, and whatever happens there is Ruby behavior, and that's how Ruby's going to behave. But what would be the downside? So yeah, so here it's precisely specified if you give it an input. But what are some downsides? Yeah.
Testing by example doesn't really let you understand the edges of what something really is.
Yeah, so let's say fuzzy edge cases, right? So, and kind of related there, so how do you know? So let's say you test some edge case, it does X, Y, and Z, whatever, it doesn't matter. Is that actually how the language developer intended that to work, or is it a bug actually in the reference implementation? So what would happen if there's bugs in the reference implementation?
Bugs in the program.
There'd be bugs in the program, but what happens so you've released Ruby 1.0, whatever. Let's say you want to fix some weird edge case. Can you do that?
Well, yeah, if they update the interpreter, then your programs might not work anymore because.
Yeah, so you gotta think you've released this program. People may be writing software that relies on this behavior because this is the reference implementation. This is Ruby. So if you change that behavior, you could break applications that are relying on those edge cases, which are really a bug, which you didn't intend. But now it's kind of, well, that is Ruby. That's the Ruby language. So you have to be very careful as far as maybe updating to Ruby 2.0, having it be rethought out and redone, or you have to analyze use cases, and it's all kinds of crazy stuff to say, well, maybe if I can hopefully show that very, very, very small percentage of people are relying on this one feature, then maybe I can fix it or change it. But yeah, you have bugs become part of the language in essence, oftentimes. What are some so what about if I write a language, an interpreter for a language, and I write it in, let's say, I write it in C, but I write it on Linux, and nobody in here only has access to Windows machines, but let's say you did, right? Is that a problem? I don't know, is it good, is it bad? I say screw you, doesn't matter. Yeah, or maybe it just straight up doesn't run on your system, right? And so here's this language. How are you going to write a program in a language where you can't even run the interpreter, because the interpreter is the only definition of the semantics of that language? If you had a document, right, if you had a 500-page document, if you were stuck on a desert island with a super weird computer architecture set, you could take the C, and just the C documentation, you could write C programs on paper, right? And by checking the documentation, you could validate and verify that they are actually accurate C programs and that they should do exactly what that specification says. When you get to a computer, you can type all that up and compile it, right? So you could do that. It would be terrible, but you could, right? But with this reference implementation, you can never run it on your system, so you can't tell if it's valid or not valid or how it should behave or not behave. So yeah, that's to me one of the real downsides here. It's kind of the portability of the reference implementation. Okay, so for formal specifications, it's actually kind of cool. So you specify the semantics of the language constructs formally. And there's different approaches. I'll show you an example of approach next. So what's like some pros or cons here? Yeah.
There shouldn't be any ambiguity.
The what?
There shouldn't be any ambiguity.
Yeah, so the pro would be no ambiguity, right? Everything is precisely defined, however they define it. Usually the case we'll look at here is they define kind of what people were talking about. You define some abstract machine, and then you say, okay, for every single operator in the language, this is how it works on this abstract machine. And so every implementation has to do it that way, otherwise it's not valid. And so you can very precisely define that. So yeah, so you can make sure that all parts of your languages are defined. And some other really cool side effects is you can actually then prove properties about either the language itself or about programs written in that language using the formal specification, because you know exactly the semantics of all the operations. What about downsides? Why don't we do that for everything? Sounds awesome. Yeah.
It's very
Yeah, so that's actually, it can be difficult to understand or hard to read. Definitely, probably, I don't know if I guess we could argue whether it's less difficult to read than a English specification of C. It's definitely, so I'll show you an example, and when you see it, your eyes are gonna go huge and be like, this is crazy, who would ever do this? But once you build it up piece by piece, right? Just by learning a programming language, you learn it piece by piece and by examples, and then you expand it into this big thing, and then it's not as scary, and it's actually kind of easier. It can be easy-ish to understand. So this is an example of JavaScript. So this is JavaScript formally specified by Professor Ben Hardikoff and his students at UC Santa Barbara. He was on my PhD committee. So this is their abstract interpretation semantics for JavaScript. And kind of, I don't know, I can give you like a brief overview. You basically have, you're specifying for each operation how you change the state of the machine, where a machine is specified by like a set of names and locations and values. And on this column here, you have all the operators in the language that are specified formally and operations. And here, let's see, what's this? Premises. This is this is specifying an if condition. And so this is like the if condition. If this condition is true, then these are the exit values of executing that function. So is this super easy to understand? No, it should not. I mean, it should not be, right? You have to like study this for a while to understand what it all means. But the point is to show you that you can do it, and then you can do cool things like having a provably sound static analysis system for a crazy language like JavaScript. Because JavaScript is very dynamic and very weird. Any questions on this? Okay. So we talked kind of at a high level what semantics is. We talked about maybe some of the ways we can define the semantics of a language. But what kind of drilling down, right? So what are the things that we care about semantically? So what do we need to give semantic meaning to in a programming language? This is not rhetorical. Anybody? What are some things you need to know? Yeah.
Conditional statements.
Conditional statements? What do conditional statements do? Is it kind of even related to that? How do the Boolean operators work? The double ampersands and the double ors, right? In most languages, it's short circuit evaluation. So you know when you write a program, you can rely on that and have cases that are maybe, you know that this second clause is only going to execute if the first clause is false in an and statement. So you can rely on that behavior. Whereas in another language, it could be the semantics of that language that it executes every single thing in an or an and statement. What else? That's a good, actually that's a good example also about ifs. There's other languages that define if and also define an unless operator. So it's exactly the opposite of an if. So unless this statement is true, execute the following code. So in some cases it can actually improve readability because you don't have if not this thing, then do this, right? Then you have to think about, oh, that's only going to happen if that condition is not true. You can say unless this condition, then do this. What else? What other things? Yeah.
You got typing or the strong type.
Yeah, typing. So what are the typing rules? So do we even have types? How do types work? How are they defined? What can we automatically translate between certain types? Can we do that? Can we not? Do we have to specify? How do we cast types? What does that mean? Yeah, types, definitely. What else? Yeah. Memory management. Yeah, so I'll kind of throw that under variables, but yeah, so kind of any variables, naming, how do variable names work? How do we refer to variables in another file, in another program? How do we link, can we even do that? Is it impossible? How do we call other functions that other people wrote in other libraries? So yeah, variables, and then memory management, when do things get freed, when do they not get freed, that kind of stuff. Where does that come from? Do we have to worry about that or do we not? Like we could use a language where we don't have to worry about that. What else? What other parts of languages do you need to know about? Yeah.
Operations.
What was it?
Operations.
Operations? In what sense?
Like an integer and an integer,
Yeah, so so the semantics of all the operators. So the plus operator, the subtraction operator. In some languages, those are actually defined as functions. So there's a function called plus, and they have a certain syntax to say, hey, you can actually, this can be an infix operator, so you can do something plus something else. Or you can just call it plus bracket something something. So yeah, that's the built-in operators. There's going to be some built-in operators. If you think about C, what does the star mean? What does the ampersand mean? What else? Is that it? Do we have other? Yeah.
Functions.
Yeah, functions. How do function calls work? In some languages, you only have procedures, right? So functions can't call other functions. You just call one function, it does something, and then returns. It's done, right? So that would be one part of the semantics. What does it mean? Anything else? Is that it? Yeah. What was it? Scope mappings. Yeah, we're gonna get into that. So yeah, kind of under variables. So how long are how can you refer to a variable by name, and how long is that name valid for? Nobody mentioned. So what about? So we talked about functions. What about I guess this is kind of maybe contained in functions. What are you passing into functions? Parameters, right? How does that work? How are parameters passed to functions? Does the function get a copy of that parameter? Can it change that parameter that you pass in so that the callee can now see that change? So what are the semantics of parameters? Okay, so we talked about types, we talked about operators. What other kind of language features do we like in, let's say, more, higher level languages? Yeah. Scoping? Yeah, that's under variables. We're gonna actually get to that next. What was it? Comments? Ooh. I'd say that depends on the language, right? So yeah, in a lot of languages, comments are just syntactic elements that basically are white space. But in a language like Python, the doc strings on each of the functions are actually part of the metadata of the function. And you can actually, I think, query at runtime the document strings of the function. So yeah, in that case, that would be those comments are part of the language semantics. Yeah. Yeah. Conditionals. Yeah, so I'd say conditionals, while statements, do whiles if there's a do while. How do those work? What are the semantics there? When do they execute? When do they not execute? What happens to, you gotta kind of think back to when you were first learning about programming. All these things you learned about, right, had some semantic meaning, and you were just learning it as that's the Java thing. This is how programming works. But then when you learn another language, it's like, oh, this is something, this does things differently. What about exceptions? Right? How does exception handling work? Do you have to do, is your language like Java, where you have to precisely define what exceptions can be thrown from your function so that anybody that calls you has to catch those exact exceptions? Exceptions can be very crazy. You can have, in some languages, if there's an exception, it goes back up the stack. That caller can then do something and then actually go back to the function that had an exception and continue execution. So you can have like all kinds of crazy stuff. So yeah, we talked about control structures. Something else around there, constants, right? So are there constants? Like in C++, you can specify that certain variables are const, which means that they shouldn't be changed. Whether that actually is enforced or not depends on the language specifications itself. And method in here. Oh, so yeah, we missed like object orientation, right? So how do classes work? How do methods of classes work? What happens when we have subclasses? How does inheritance work? How do we know which function is going to get called in the object orientation hierarchy? Yeah.
So what would like visibility fall under this?
Yeah, visibility. That would be, I'd put it under the classes. So that's a thing that specifies, what can you access from a class, from outside that class, from subclasses or child classes, all that kind of stuff. So these are all the things that we've got to define. Yeah.
What about keywords?
Keywords. Yeah, that's actually really good. I don't think it's on here. I don't think it's on this list, but yeah, what are the so you got to think of it kind of as like the built-ins, right, or the keywords. So what do these keywords mean? So I guess the other thing to point out that's not on here, it's not really, we don't really care about the standard library at this point. So like the standard API functions, like we don't care. We're talking about C, we don't really care about printf or those kinds of things. They should have documentation, but however they work, right, still has to specify to these language semantics because we're calling some C or C, whatever, it's just a function. So here we're talking about what is the semantics of the language itself. Yeah?
What about statements and expressions?
Statements and expressions. Yeah, that's a good point. That's not on here. So there's various rules. Like in Java, you can't assign inside of an expression. So inside an if or while statement, you can't assign a variable. But in C and C++, you can. And that can also cause some confusions and problems. Yeah, that's good. Okay, so we're going to start with variables. So we're going to touch on a lot of these areas. And what I kind of really want you to focus on and to get out of this is that these are all more or less arbitrary decisions that a person or a team made when designing these languages. So these things aren't set in stone. It's not that all languages have to be like this. We're going to kind of talk about some of the standard semantics of these different aspects. So the first thing we're talking about is declarations. So some constructs, like we know, have to be declared before they're used, right? So if you think about variables, variables are a construct, and in some languages, like C or C++, we have to actually define that construct. We have to define a variable before we can use it. And often we want to associate the declaration with a specific name. So we want to give it a name. So we want to say, I'm declaring a variable food here, and it has a type integer. And this is how I specify that in the language. And so this would be it. Like, here's an integer I. So this is a variable declaration. We're declaring a variable whose name is I, who has an attribute that it's an integer. So it has the type int. A specific type int, but we can think of it as a type integer. But this isn't the only way we can write a language, right? So how does Python do declaration, do variables? Or I want to say Perl is similar, but I don't know enough to make that claim. Or another language, yeah.
Python doesn't treat names as variables, they treat names as names, and depending on
So I'm not talking about type. So type's just an attribute of a name, right? So it's still a variable, right? Because we can assign to it, we can change it, but you don't have to specify it. You don't have to declare it before you use it, right? You just say, hey, this new target is equal to test value plus 10. So now target is just a new variable. So this can be handy because you don't have to say, I'm in this function or this block, I'm going to use a variable called target and a variable called test value and a variable called this. You can just say, when you need it, it will automatically create a new variable for you. A downside here is that if you then accidentally fat finger target and forget the A or something, or add an extra A, it'll gladly create a new variable for you, and your program just continues and goes but does the wrong thing, which I've personally done a lot. Okay, so the main question when we're talking about variables is, so this is what we're talking about with scoping rules. So once a name is declared, so once we've declared some variable, how long is that declaration valid, and what other places can refer to that same declaration by name? So what are some options? Global? So yeah, you could think of a programming language where I would say maybe, well, depends on how global you want to get. So like the entire program can access that variable name. You could actually think of a programming language where every variable declared is accessible by anything in your program. It could happen. What are some other, like, let's say boundaries or lengths that you could do? Yeah?
Private.
Private, so in that case, only your class, only in that class definition, and so it could be the same file, it could be different files depending on how the classes are defined. Yeah, what else? Was that? Only a function? Yeah, so what about some variable? Sometimes we only want it to be in a specific function. What about for just an entire file? Right? What if we don't want, so it's kind of like the private variable, we don't want other files to be able to refer to our variables, but we want this file. So in this case, it's at like the file level is how things are valid. What about like really global? So think about something crazy. It's like if you had to write variables that referred to every program that was ever written in that language. Right? So you'd write some variable and it would be globally accessible to anybody ever. Does this ever happen? It's not really in the case of programming languages, but that you have to contest with other people and make names that are super unique. Yeah. APIs like APIs called by a third party, like maybe you need some. Yeah, so usually I'd say they're namespaced by whatever API you're using. What about more global? Yeah.
IP addresses.
IP addresses, yeah, that's a good one. What about on top of IP addresses? Ports? I'd say ports are mapped to IP, so we could have two different ports that refer to the different machines. What about, how do you get to an IP address? Yeah.
Hostname?
Hostname, yeah, so DNS, right? DNS is a global system where you have to declare a globally unique identifier. Anybody do mobile development? Yeah, so what about there that has to be global?
Web services.
Web services, kind of. I'm thinking more like the package names of Android applications have to be global. So global in the sense that it has to be marketplace-wide unique. And so that's why you get things like the Facebook app's name is like, most Android apps are like com.something. And so this is how you get that. So we talked about function. And so the flip side of this question is when we see a name, how do we map it back to the declaration that refers to? And so we talked about it, so scope is what we call this. So what's the scope that this declaration can be referred to? And so there's two important things here in scope: how long a declaration is valid for, and how to resolve a name. So when we see a name, how do we know what declaration that refers to? So this is a good stopping point for this time. Thanks everybody, see you on Monday.